This is the February-March 2025 paper, and this is the data that we have, right? And these are the list of formulae, as you can see here. So let's move towards the first question here, which is a question number 1. A steel ball is placed on the inside surface of a hollow circular cone, right? As you can see here, the ball moves in a horizontal circle at constant speed as shown in figure 1.1. The side of the cone to the horizontal is 52 degrees, as you can see. There is no friction between the ball and the cone. Figure 1.2 shows a cross section through the cone and the steel ball, right? So this is the cross section that you can see here. On figure 1.2, draw labeled arrows to show two forces acting on the ball. So we have one force which is acting here, which is the weight, right? Which is exactly downwards. And the other force that we have is the normal reaction, which is this. We call this the weight. And this is the normal contact force here. It's perpendicular to the boundary. Describe how the forces acting on the ball causes its acceleration to be centripetal. So you should know that the vertical component of the contact force basically does what it supports the weight, and the horizontal component of the contact force provides the centripetal force, right, which causes centripetal acceleration towards the center. So what's going to happen here is basically this. If we have something of this sort, this is the component which is which balances the weight, and this component precisely is about the centripetal force, right, towards the center of the circle. So I'm going to write here that the vertical component of the contact force is equal to the weight. So there is no resultant force vertically, right? So you should know this, that the horizontal component of contact force is the resultant force towards the center of the circle, which causes centripetal acceleration. Next part is the ball moves in a circle of radius 0.15 meters. Show that the speed of the ball is 1.4 meter per second. So if you look closely here, this is 52 degrees, right? And this is also going to be 52 degrees since they are alternate angles. And since this is 90 degrees, this part here, normal contact at this boundary, this here is going to be 38 degrees, right? We have called this R. Now you know that this R sine theta, which is this R sine 38, that is equivalent to the weight, which is mg. And R sine of 38 here is equivalent to the centripetal force. So what you're going to do here is that you know that R, as we've seen here, that R sine 38 is equal to the weight, is mg. And you've seen that R, the sine of 38, is equal to the centripetal force, which is the resultant force, so it's ma. And we also know that A is equal to V square over R, right? What you can do is this R is going to cancel with this one, this M is going to cancel with this one. Since we're going to divide this R sine 38 with R cos 38, and we're going to divide this with this one. So this is sine theta over cos theta is tangent theta. So this is tangent 38 degrees. is equal to G over A, and this A is equivalent to G over, tangent 38 degrees, right? And once you substitute here in this formula, you will get your answer for this speed. A is 9.81, G is 9.81, tangent 38 times the radius, which is 0.15 meters. We go here is equal to V square. So V is going to be square root of this entire thing, 9.81 over tangent 38 times 0.15, and you'll get your answer as 1.4. The next part is calculate the angular speed omega of the ball. So you know that V is equal to R omega, right? And you know that V is 1.4 here, or you can use 1.37 because we rounded off it to 1.4. So, it's 1.37 here, and the radius is 0.15 times omega, and omega is going to be 1.37 divided by 0.15, and omega is going to be 9.1 radians per second. The ball is increased. Explain why the radius of the circular path of the ball increases. Uh, for this, you should know that since it's the same resultant force, right? And we have got the same acceleration as well for that. So if speed increases by this formula, A is equal to V square over R, the radius of the circular path also increases, right? So if this increases, this also increases, and the acceleration is constant, right? So what you'll write here is that uh, we have the same resulting force. So there is same acceleration, right? And if the acceleration is the same, so if speed increases, for example, the radius must also increase. Moving on towards question number 2. Magnitude of the gravitational potential on the surface of a planet of radius r is pi. The planet can be considered to be an isolated sphere. On figure 2.1, sketch the variation of the gravitational potential with distance x from the center of the planet for values of x between r and 4r. What's going to happen is that at r, you know that phi is the gravitational potential and it is given by minus gm over r, right? And you should know that this thing is going to remain constant gm, so it's going to be minus phi times r is equal to gm, right? So you should know that at r we have minus phi, right? And what's going to happen at 2r, right? Uh, if you write here 2r, then this should be minus phi by 2 in order to get the same answer, in order to get gm. So we have another point here, and then you should know that we have again we have to get the same answer. So when we have 3r, we have minus phi by 3 times 3r, we get the same answer gm. And at 4r, we'll apply the same concept. This is minus phi over 4 times 4r, and that will give us the same answer. You can see here as gm, because this 4 will cancel with this 4, and you get the same thing, right? So at 4r, we have, this is minus half, and this is going to be something like this, and we have to plot it. The plot is going to be like this, continuous curve like this. So the next part is a satellite is in geostationary orbit above the Earth at time t0. The magnitude of the gravitational potential due to the Earth at the location of the satellite is phi. And figure 2.2 sketch the variation of the gravitational potential due to the Earth at the location of the satellite for values of t between t0 and t24 hours. What you should consider is that since the formula for the gravitational potential phi is minus gm over r, right? And the gravitational potential is negative, you know that. Uh, so, and we know that the radius for geostationary satellite is constant. So the line is going to be like this. It will be a straight horizontal line, which is like this. We get a line like this. It's going to be a constant straight line. The electric potential difference between two parallel plates is V, as shown in figure 2.3. The distance between the plates is D. The region between the plates is a vacuum. On figure 2.4, sketch the variation of the electric potential with distance from the positive plate. So what's going to happen is that you have to, you know that the electric potential is maximum at the positive plate, right? And as we move towards the negative plate, the potential is going to decrease. And it's going to be a straight line, starts from here, and it's going to be like this. So it will be a straight line all the way till T. Straight line all the way from this to this. Question number 3 is two metal cuboids P and Q are in thermal contact with each other. P and Q are in thermal equilibrium. State what is meant by the term thermal equilibrium. So when P and Q are in thermal equilibrium, they have the same temperature, right? There is no net transfer of thermal energy between P and Q. I'm going to write here that P and Q have the same temperature is no net transfer of thermal energy. Data for P and Q are given in table 3.1. P and Q are initially both at the same temperature. P is supplied with 24 kilojoules of thermal energy. After some time, P and Q are once again both at the same temperature as each other. P and Q are perfectly insulated from the surroundings. Determine the change in temperature delta T of Q. So you should know that here what's happening is that P is being supplied with 24 kilojoules of thermal energy, right? And what happens is that initially they are both at the same temperature. And again, what happens is that after some time, they are again at both the same temperature as each other, right? Uh, so let's talk about the change in temperature of Q. You know that the Q is equal to MC delta theta delta T, right? And the energy that is being supplied here is what? That is 24 kilojoules. So this is going to be 24 into 10 raised to power 3. The mass of the P that we have is 0.54 times the specific capacity that is 390. And of course, there is a change in temperature of that as well. Because after some time, P and Q are once again both at the same temperature with each other. Right? So there is a change of temperature, that is delta T. Also, you know that since the energy is being supplied here, there is also the energy gain for Q, which is again going to be 0.37 times 910 times delta T. And once you solve this, right, you get the temperature delta T as 44 Kelvin. It's 43.9, and you can write here two significant figures there as 44 Kelvin. assumed to be an ideal gas. A fixed amount of nitrogen gas is contained at a constant pressure of 1.6 into 10 raised to power 5 Pascal. The variation of the volume of the gas with temperature of the gas is shown in figure 3.1. Temperature of the nitrogen gas is increased from 0 to 210 degrees Celsius. Determine the work done on the gas. So the formula that you'll apply here, it's thermal expansion. So, the work done is going to be negative. The work done is going to be delta E. And you know that the pressure is constant, that is given here. It's 1.6 into 10 raised to power 5. And the change in volume that you'll see here, it goes from, 0 to 210, right? So, you know that it's going to be somewhere here. And it goes like this. The value here is 0.32, right? At 210, the value of the volume is 0.32, right? This one. So it's going to be 0.18 minus 0.32, like what we get, minus 2.2 into 10 raised to power 4 joules Henry. This is a negative work done because it is expansion. Determine the number of molecules of nitrogen gas. You'll apply the formula PV is equal to NKT. Okay? And this is going to be what? This is going to be PV over PT. And you have here the pressure as 1.6 into 10 raised to power 5 Pascal times the volume. Let's say we take one temperature here, that is 0. The volume here is 0.18. Then we have the Boltzmann constant is K, which is 1.38 times 10 raised to power minus 23. And the temperature should be in Kelvin. It should not be in degrees Celsius. It must be in Kelvin. And you know that the temperature conversion will lead to 273 Kelvins. 0 degrees Celsius is basically 273 Kelvin. You get your answer here as 7.6 into 10 raised to power 24. The mass of nitrogen molecule is 4.7 into 10 raised to power minus 26 kilograms. Calculate the root mean square speed of the nitrogen molecule at 210 degrees Celsius. So you should know that it's going to be half mc square. You know that the kinetic energy, average kinetic energy is equal to 3 over 2 kT. In order to calculate the RMS speed, what you can do is this 2 is going to cancel with this one. C squared average is 3 kT over m. And you're going to take the square root on both sides. You're going to be CRMS is under root P kT over m. So K is what? That is the Boltzmann constant, and that is 1.38 into 10 raised to power minus 23 times temperature. Temperature, you should know that at 210, you have to convert that into kelvins. So 210 plus 273 divided by the mass of a nitrogen molecule. Remember that this is the average kinetic energy of one molecule. So the mass of nitrogen molecule is this. So this is going to be 4.7 into 10 raised to power minus 26. And the RMS speed that we get here is, correct to two significant figures, is 650 meters per second. All crystal is made to vibrate with simple harmonic motion. The variation with time of the displacement x of one surface of the crystal from its equilibrium position is shown in figure 4.1. You can see here that this is simple harmonic motion. Show that the angular frequency of the vibration of the surface is 4.2 into 10 raised to power 7 radian per second. So what you'll do is, you know that the omega is 2 pi over capital T, which is the period. You can see here clearly the period here is 0.15 into 10 raised to the power minus 6, right? This is one complete cycle. So omega is going to be what? 2 pi capital T is what? It's 0.15 times 10 raised to the power minus 6. And you'll get your answer here, which is 4.2 into 10 raised to the power 7 radians per second. Determine the maximum acceleration of the vibration of the surface. So what you can do here is that the acceleration is going to be A naught here is omega square x naught. X naught here is the amplitude here. This is the formula for the maximum acceleration. So omega, you've already calculated here. 4.2 into 10 raised to the power 7 whole square. And x naught is the amplitude, and you can see clearly here it's 40 into 10 raised to the power minus 6. Answer is going to be 7.1 10 meter per second square. It may be modeled as a single mass of 2.4 into 10 raised to the power minus 4 kilogram that vibrates as shown in figure 4.1. Calculate the total energy of the vibrations. You know this, that the formula for the total energy is half m omega square x naught square, where x naught is the amplitude. So you have all the information here. You have the mass. Omega is, you've already calculated that, that is 4.2 into 10 raised to the power 7 square. X naught here is, and you'll get your answer in two significant figures as 340 joules. Generates ultrasound waves that are used to obtain diagnostic information about internal structures. The crystal is made from piezoelectric material. Explain how the crystal is made to vibrate. So what happens is that the crystal is, you know, uh, there is some alternating potential difference which is being applied to the crystal. And what happens is that when you apply this, that causes the crystal to distort, right? And that causes vibrations of the crystal. What happens is that crystal is made to vibrate by applying alternating potential difference, E dot D dot. What happens is that applying alternating difference across the crystal causes it to distort. That, produces compressions and rarefactions, and this produces vibrations. A little beam of ultrasound wave is incident on a muscle bone boundary. Data for muscle and bone are given in table 4.1. So we have the muscle here, the density is given, the speed of sound is given, bone is there, speed of sound is given. Calculate the percentage of the intensity of the ultrasound beam that is transmitted at this boundary. So what's going to happen is that we know very well that uh, Z is the specific acoustic impedance, and that is given by rho C. And intensity reflection coefficient for the muscle bone boundary can be calculated by this formula. It's also given in the data sheet. At the top, you can see uh, right here, Z for muscle is going to be what? It's going to be rho C, where rho is the density and C is the speed of sound, which is the ultrasound here. And we have here 1100 times 1600, which is equivalent to 1.76 into 10 to the power 6 for the muscle. And for the bone, we have again 1900 times 4100, and that is going to be 7.79 into 10 raised to the power 6. So once we have this, you can find the intensity reflection coefficient alpha as I or I naught. That is going to be equivalent to what? You know that it's given by uh, z1 minus z2 whole square over z1 plus z2 whole square. So what we can do is we can take z1 as zd, and that is going to be 7.79, right? We can ignore 10 raised to power 6 because it's going to get cancelled anyway, right? Because this is also 10 raised to power 6 and this is also 10 raised to power 6. 7.79 minus 1.76 whole square, and that gives us a value of 0.40. This is reflection. However, we have to find transmission. So transmission is going to be 1 minus alpha, which is going to be 1 minus 0.40. That is 0.60 in terms of percentage. It's going to be 60%. We multiply it with 100. Question number 5 is a capacitor of capacitance C1 is connected in series with a second capacitor of capacitance C2. Show that the combined capacitance of the two capacitors is given by this formula. So this is a very important derivation here. You have here one capacitor like this. You have another capacitor like this. You should know that the charge is the same. That is going to be on both of these capacitors, right? The total charge, if you want to make a single capacitor like this, the charge Q is equal to Q1 and Q2. So Q1, Q2, and Q are equal, right? But however, if the potential difference here is V, this is V1, let's say this is V2, you should know that uh, V is going to be equivalent to V1 plus V2. And also you should know that Q is equal to Q1, which is equal to Q2. So V is going to be equivalent to Q over C. V1 is going to be equivalent to Q over C1. You have, this is going to be Q over C2. We know this very well that Q is equal to CV, right? So we have used that formula. You take Q common here, 1 over C, going to be 1 over C1 plus C2. This Q is going to cancel with this one. You get 1 over C is equal to 1 over C1 plus 1 over C2. Three identical capacitors, each of capacitance C, are connected in a network as shown in figure 5.1. The variation of the charge Q with the potential difference between the terminals X and Y is shown in figure 5.2. So you have this QV graph here, and show that C is equal to 44 microfarad. In this question, you have to realize here that the gradient of QV graph will give you the capacitance of the entire network. You know that Q is equal to CV, so QV is equal to C. So if you look closely here, this is C. These two capacitors, they are here in series. So what's going to happen is that the capacitance here for this and this is going to be half C, because 1 over C is 1 over C plus 1 over C. And the total capacitance for both of these is going to be C over 2 if you take the reciprocal. This is C over 2, the total capacitance of both of these, right? And you know that this C and this C by 2 they are in parallel. So the total capacitance, since in parallel, you know that they're simply added. Capacitance is going to be C plus C by 2, which is equivalent to, 3 by 2C, right? Also, if you look here very closely, the gradient of this is going to be 400 into 10 raised to power minus 6 over 6. So the gradient, according to this graph, 400 and 10 raised to power minus 6 over 6. That is the gradient. And you equate it with 3 over 2C, and you can find the value of C like that. So 3 over 2C, the total capacitance is equal to the gradient, which is 400 times 10 raised to the power minus 6 over 6. And precisely the value of c is going to be what? 2 into 400 is going to be 3 into 6. And the answer is going to be 44 microfarad. The capacitor network in 5.1 is charged and then connected to a resistor of resistance 54 kilo ohms. The capacitor network discharges to the resistor. Determine the time constant of the circuit and give a unit with your answer. You know very well the time constant tau is equivalent to RC, and the R is the resistance of the entire network. The resistor and the capacitance for the entire network is 44. So we have 54 here into 10 raised to the power 3 times C, which is, you know, that is going to be 3 over 2 times this 44 into 10 raised to the power minus 6, because it was 3 over 2C for the entire network, you know that. So it's going to be equivalent to 3.6 seconds and 2 seconds. And it's the time constant, so the units are seconds. Determine the time taken for the discharge current to reduce to 15% of the initial discharge current. So the formula for this is, you know that it's I is equal to I naught exponential minus T over RC. And since it reduces to 15% of the initial value, so I over I naught is equivalent to E minus T over RC. And this I over I naught is going to be 0.15 because it reduces to 15%, right? We have here RC as 3.6, and we can use mathematics here. We can take natural log on both sides. So this is ln 0.15, ln exponential minus t over 3.6. This is ln 0.15, and this is going to be minus t over 3.6, and the value of t is going to be 6.8 seconds.